A dipole moment results when a molecule has a center of positive charge separate from a center of negative charge. So we've talked about HF before and how the electrons are shared unequally. They're closer to fluorine because fluorine is more electronegative. That creates the partial negative on the fluorine, and that creates the partial positive on hydrogen. And so this is said to have a dipole moment because it has one positive end and one negative end, and you can draw it like that when you kind of make a plus sign on the positive and then the arrow points towards the negative. So the plus sign really goes on the side with the less electronegative element, and the arrow points at the more electronegative element. Water has a very important dipole moment. You probably have talked about water being polar in biology. And so the fact that water is polar allows it to do something called hydrogen bond, which then gives it all of those properties that you've learned about previously, like adhesion, cohesion, high surface tension, high melting point, high boiling point, all that stuff. So really what's going on here is oxygen's more electronegative than hydrogen. And so on each hydrogen, there is a dipole moment. And they kind of add together. So you have they're both pointing at the oxygen. They kind of add together to make one big dipole moment that goes that way. So water is known as the universal solvent. It can dissolve most things, but it can't dissolve everything. Water can't dissolve oil, for example. And this comes down to a concept called like dissolves like, whereas water, which is polar, as we know, can only dissolve other polar things or ionic things. So it has to have some kind of charge that the water molecule can grab onto in order for it to dissolve it. It cannot dissolve nonpolar things because there's no charge for that polar water molecule to grab onto. Like I said, water, this dipole moment of water allows it to do something called hydrogen bonding. The hydrogen bonding allows the water molecules to stick together, which makes water liquid at room temperature. Water shouldn't be a liquid at room temperature. Other similar compounds are not liquid at room temperature, but the fact that it has this strong dipole moment and hydrogen bonds is what allows it to be liquid at room temperature. So in a polar bond, electrons are shared unequally. The more electronegative atom is going to pull electrons closer to it and therefore will have a slightly negative charge. The less electronegative atom will have a slightly positive charge. So carbon dioxide, for example, oxygen is more electronegative than carbon. We know at this point that it's a double bond, right? Because we've done this molecule quite a few times. And so the oxygen is going to pull the electrons closer to it. So each oxygen will have a partially negative charge and the carbon will have a partially positive charge. If I were to draw the dipoles, the positive would be the carbon. And so you look at each bond individually. And so both dipoles are going to start at the carbon and then point out to the oxygens. Having a polar bond does not necessarily mean that a molecule is polar. In order for a molecule to be polar, it has to have at least one polar covalent bond, and it has to have asymmetric geometry, so not symmetric geometry. You could be asymmetric by there being lone pairs on the center atom, which is going to make it bent or trigonal pyramid. Or you could have different atoms bonded to the central atom, like CH3Cl, where you have hydrogen on one end and chlorine on the other end. So this bear is polar because he has a definitive dipole moment. He has one side that's positive. He has one side that's negative. So this is a polar bear because you have one positive side and one negative side. And you have a dipole moment in just one direction. So this is also what makes molecules polar. So HCl, if I do the Lewis structure, looks like that. Chlorine is more electronegative than hydrogen, so chlorine would be the partially negative, hydrogen would be the partially positive, and so I do have that definitive dipole pointing in one direction, and so this is a polar molecule. We're going to skip water for a second. So like I said, though, just having a polar bond does not necessarily make a molecule polar. So we'll look at CH4, methane. So carbon is more electronegative than hydrogen. So each one of these hydrogens, if I draw the dipole moment for each one, they're pointing in at the carbon. There's not one definitive, this is the dipole moment going in this direction. And so when that happens, even if there's polar bonds, which is what causes that dipole moment, it is a nonpolar molecule. Another example of this would be carbon dioxide, where we know the oxygen is more electronegative than the carbon. And so my dipole moment would point that way and that way. So they're both pointing out. So again, there's no definitive, this is the direction of the dipole moment. And so this is a nonpolar molecule. So again, a polar bond is when electrons are shared unequally, but a polar molecule has a definitive dipole moment. One side is partially positive, one side is partially negative, and shape is going to play a big role in this. So if I look at NH3, typically ammonia is drawn like this. And if I draw ammonia like this, I might be incorrect when I'm determining if this is a polar molecule or not, because nitrogen is more electronegative. So it looks like I don't have a dipole moment pointing in any one direction. But this is a trigonal pyramid shape because of that lone pair. So really, the nitrogen's on the top and the hydrogens are on the bottom. And when I draw it in the shape, it's easier to see this dipole moment. Oh, they're all kind of pointing up at the nitrogen. And so I have this dipole moment that goes like that. And so this is definitely a polar molecule. If I have something like CCl4, all the chlorines would have lone pairs all the way around. Chlorine is more electronegative than carbon. So they're all going to be pointing out. And so again, this would be a nonpolar molecule because there is no one direction that the dipole is pointing. If I have something like CH3Cl, H, Cl down on the bottom. Carbon is more electronegative than hydrogen, so those would point towards the carbon. But chlorine is more electronegative. So you look at each bond individually and you do a dipole for each bond and you kind of see what happens and what they add up to. So chlorine is more electronegative than chlorine is more electronegative than carbon. So it has a dipole that goes that way. And if you look, I got two pointing down. So I actually do have a definitive dipole that goes from the top to the bottom. And so this is a polar molecule. So again, the shape, like I did with the ammonia, the shape is very important. If I don't draw water in the correct shape, I might think, oh, look at that, it's nonpolar. But we know that that's not the shape of water, right? Water is bent. And so we have the dipole moment going that way, and we have the dipole moment going that way. And so they add together, and definitely we have a dipole moment pointing up towards the oxygen. And so water is a polar molecule.